coming. So this is talking about Apache Spark. I know that the title was Big Data Pipeline condensed. Really, the focus is a little more on Apache Spark. So sorry, I hope people know what they're getting into here. My name is Aman Rashid. I'm with Cloudera. I also spent the last 5-6 years building various kind of ETL style pipelines using Apache Hadoop and also Spark recently. I've been at Cloudera for the past 5 months, where I spend my time working on Spark as well. So, and also Guru up here is in front. He's another member of Cloudera, so he might be able to answer questions as well. So, just to give you some idea what we talk about. We're going to do just a high-level overview of what Spark's about, kind of how it fits into the whole big data space, all the, if you've heard some of the different terms out there, what this is about. We'll jump right into some example programs, see what you can do with Spark. Very intro level. Don't expect any, super fancy things, but just kind of get your feet wet and see what it's about. And then we'll step back and go, well, what did we just do? What's Spark's compute model? How did this work? Why is this a useful thing? See some common mistakes which I see people make, and then a little bit about the scale. Also, there may be too much material here, maybe there's not. We'll get through it all. And so feel free to interrupt and ask questions. I don't, we'll make it as far as we get. It's fine with me. So just very, very generally, I want to make sure we're all on the same page. Just what this this big data problem is about. So, there's all sorts of big data sets out there. There's everything from web transaction data, weblogs, who's visiting what. This is the Googles and the Facebooks of the world, and how many people are visiting what. To online transactions, to online advertising, who's viewing what ads, who's purchasing what ads. These data sets very quickly grow beyond the capacities of a single machine, right? Sure as your data sets start to grow, machines are bigger and more powerful every day, but these data sets quickly surpass that. You might start with a 10 gig data set, and next month it's 100 gigs, and then terabytes, and very, very quickly you grow beyond what a single machine can handle. And so one of the key tenets of a lot of these technologies is to be able to scale horizontally. That is, as your data set grows, you don't want to be like, well, let's see, we just, we bought the biggest machine we could today. If we wait a month, then maybe there's going to be a bigger machine, and hopefully that'll get us just a little bit further. You want to be able to say, okay, we're running out of capacity. Let's just buy more computers. Obviously, that's spending money on more computers, but that's a lot easier than just having no other solution or being forced to, with a very tight time deadline, being forced to re-architect everything. Like, well, maybe we can squeeze more horsepower out of what we have. And also, you want a simple programming model. So doing distributed computing is hard, right? You've got to deal with a lot of issues. You want to be able to have something which you can reason about, think about still very much the way you think about a single-threaded, simple program, but have it scale to work pretty similarly on lots of nodes, be easy to think about, easy to reason about, easy to debug, and also be fault tolerant. So as you get to large clusters, things going wrong is the norm. We have a lot of customers with hundreds of nodes of clusters and hundreds of nodes in their cluster, and some disks are going to be bad. That's just a given. And you need to have a system which can deal with that. And you don't want, as the application developer, to have to deal with that logic. Oh, well, send this request there, but maybe if that node's not doing well, we need to deal with it. I mean, it's not something you want to deal with. So along came MapReduce, and the basic idea was that you kind of got 3 phases of work. So data lived out in your cluster somewhere, and first you would have some map phase. Each node in your cluster would have some set of data. It would do some simple transformation, a map transformation. It would do whatever it would do. It would read that input from disk. Then it would do the shuffle phase. So really, it's kind of better named map shuffle reduce. So the shuffle phase, the idea is that the map is each node is working independently. In shuffle, you're kind of grouping the data together. And so that's in the kind of diagram you see all the blue records go together, all the green records go together, all the yellow records go together. And then reduce is one final. Now you've got the data grouped together. You can do one final transformation on it, and then you write it out to disk again. And you get fault tolerance by replication. So if a disk goes bad, it's okay because you've got another copy of that data somewhere else. And again, the system handles that for you. You don't need to worry about that as the application developer. You say, read all my data, and the system figures it out. So problem solved, right? Looks like MapReduce has got it covered. Well, it kind of, but there are a couple of things that aren't great about it. So first of all, the API is really cumbersome. I don't know. Actually, I should just. How many people have used Hadoop MapReduce? Is this common or not great? Has anybody used Apache Spark? Or is it, okay, just a little bit. All right, cool. Right. So those of you who used Hadoop maybe you're used to it, or maybe not. The API is definitely sort of a headache to use. And disks are slow. Right? They're one of the slowest pieces in modern infrastructure. And it's not that hard to get machines with tons of memory right now. You can get machines with 100 gigs. It's not unreasonable at all. And so you can easily get up to many terabytes of memory in a cluster. And so you want to use that effectively, which this model just doesn't do a very good job at. The other thing too is just like from the architecture, the way it was made, the task overhead is high. It's just kind of like the way the system was built. It's not really that responsive. It's meant for when you've got to do, if you're doing some 10-hour pipeline and you're processing huge amounts of data, it doesn't matter whether you've got a 5-minute overhead. Who cares if your job's 10 hours? But it does matter if you're trying to do something that's going to take 1 minute. Well, then 5 minutes of overhead is absurd. So along came Spark. So just a little bit of background if you haven't heard of Spark before. It's an Apache project. So it actually came out of the AMP lab at UC Berkeley. Some folks there who actually had worked on done things with MapReduce, and so this was their idea to kind of have a new version of it. So it's meant to replace that compute layer of MapReduce, and it solves some of the problems. First of all, it's easy to develop. There's a lot nicer APIs. Java, Scala, Python, and R. There's an interactive shell, which I'll be demoing stuff in a little bit. And overall, it just means you need to write a lot less code. There's just a lot less boilerplate, which makes it easier for you to reason about things. And secondly, it's way faster to run. So I'll get into some more detail about what these things mean, but it uses an idea of execution graphs to let it optimize the way operations are run. It makes use of memory, which Hadoop didn't do a very good job at. And also just in general, it was re-architected. So whereas, I was saying that like the high task overhead, Spark worked to just fix that. So, we don't need that anymore. So that meant it can be faster, even faster when you're using disk, but if you take advantage of memory, you can easily get 100x. So just so you know a little bit about what else is happening in Spark. So you may have heard of some of these terms. Spark is kind of an umbrella project. There's a lot of different parts to it. So first of all, there's like the core compute engine, but then there's also a number of different projects in it. There's Spark SQL, which is a way to use SQL to query data in Spark, and also sort of a query optimizer if you're dealing with data sets which fit into a certain structured pattern. Spark Streaming for doing near real-time processing, machine learning library, graph library, etc. I'm really just going to talk about Spark Core because that's kind of a place to start. This is kind of an intro talk. Also, what I have time for and probably what I'm most familiar with too. So that's what I'm going to focus there. And the other thing too is that Spark is not meant. You may have seen, if you've heard much about Spark before, you may have heard it talked about as like the replacement for everything else that's out there. And it's meant to replace some components, but not as a total replacement. It actually lives alongside a lot of other things in the Hadoop space. So you still read your data from HDFS. You just don't necessarily always read and write it. You read it, you do a bunch of work on it, and then you write it out when you write it again. And it can also use any Hadoop input and output formats. Connectors to HBase or whatever else you have, and it can use the same cluster that you have other Hadoop components living in with Hadoop's resource manager Yarn. Any questions so far?
So what is the persistence layer for this? Is this primarily HDFS or Spark has its own?
No, well, it's primarily HDFS. But you can use whatever you want. Spark, out of it's not directly part of Spark. There is another storage layer, Tachyon FS, which is it's a little, well, this is just my opinion, but it's a little less mature. At this point, it's similar, but it still uses HDFS libraries and everything. So it feels.
So what do you see your customers using mainly?
HDFS. Yeah. It depends on the use case too, but HDFS is the.
Just wondering on the Spark SQL real quick. Is that how does that compare to Impala?
So that's a great question. So we have obviously I'm here with Cloudera, right? So we have our own angle on it. So Impala is very much. Cloudera supports Impala very much. So Impala is really designed to fit a very specific use case, and it does that very well. And it's kind of mature and tested in that use. So Impala is multi-users, very very quick queries. So a lot of kind of the standard business intelligence, I guess, analytics type use cases. Spark SQL is, again, in my opinion, it's promising, but it's not that mature yet. So for example, at Cloudera, we don't support it yet. just because we don't feel confident telling customers this is something they ain't on, right? Which, you know, that's not to say it won't get there. It's not also really exciting technology, but it's not, you know, that there are, yeah, is that answer your question?
Yeah.
Okay, so hopefully that just gives you some sense of what it's about. But now let's jump to some examples. So I'm gonna move over this window. So first, let me show you. I just have some. Whoops. I have this. This is it. I apologize in advance. This is a really dumb demo, just to get your feet wet. It's not a fancy app. But all I'm gonna do is do a little bit of querying. I have this little input file here. It's just some log4j logs. So you know, just your standard log file. And do some super queries on it if you like it. So that's all it is. I have this file sitting around, and I'm gonna fire up the Spark shell. So I'm running this example locally. So this is all running on my laptop. The reason for that is just that I'm doing a demo here and I didn't want things to go wrong. But everything I'm doing here you could do on a cluster, and I'll emphasize that again later, including the shell. You could be connecting to a cluster of 100 computers and still have this interactive shell at your fingertips for dealing with it. I should have asked another question. Any Scala developers out there? No. Okay. So this will be the first Scala. I'm going to use the Scala API. It's what I'm most familiar with, and also it's best for kind of demoing just because the code is more concise. I'll try to walk people through it, but feel free to ask questions as I go. So this what I'm doing now is this is an interactive shell, which it's really, Scala already gives you this. It's just, you know, you can do some simple math, right, of course, and you can also define some variables. Do whatever, right? It's just evaluating. That's just plain vanilla Scala code, right? And Scala gives you this for free, but the Spark shell is sort of a souped-up version, which also gives you access to some enhanced things from Spark. So what I'm going to do is add some of these nodes just right. So start with just defining where my input is. I'm going to create a data set by just saying, hey, so SC is a Spark context. Just saying load this text file. So I've got my unit test log file. And off it goes. And so you see some output. Basically what I got at the end was this thing called, it told me I had a variable called lines, which is of type an RDD of strings. Right? And this feels very much like a collection. Just kind of, the idea is that this should feel like a collection of strings. So I can get the first element, and it was some log line from that collection. I can count how many elements there are, and it will tell me there were 808 elements in there. You see that all that other logging is Spark doing its work in the meantime, but I get this interaction with it. Like it looks kind of just like a collection. So I can also do things like, well, let me filter. Okay, some of this is going to be a little bit of Scala syntax. So I'm going to say for each, I want to find how many lines were info level, right? So line that contains info. And so tell me how many of those there were. 793 of them were info log lines. How many of them were error lines? 4 of them. Okay, so it feels, again, very much like I'm working just with a collection, right? I can apply simple operations on it and see what, get some fast output. An important point here is that all of this work, this looks, again, so far this shouldn't be terribly impressive. I'm just reading a line and parsing it. But the point is that this could all be happening on a cluster of computers. The code will look exactly the same. So one thing that's happening here is that each time I read this file, I'm going to disk, right? But I can tell Spark, you know what, I'm going to read this file over and over again. I've got plenty of memory on my computer, so let me cache it in memory. So that's saying cache, just it's this primitive of Spark saying, that happens lazily. Nothing has actually happened so far in Spark. But the next time I count it, Spark is going to log the data. It's going to stick the data in memory. So yeah.
So when you load the data, when you create your context and initially and start performing your first filters and counts on it, that is not done in memory?
Correct. That is not done in memory. You have to tell Spark when you want things done in memory and when you don't. Otherwise, it won't do that. I'm going to talk about that a bit more later.
Okay.
But not, again, too much particular. So does that answer your question, though?
Yes.
Yeah. So you definitely have to tell it, yes, I want this data set stored in memory. It will not do that for you.
That's evaluated isolate.
Yes. That's right. And so after you do this, there is a UI which you can see, like, okay, well, what data sets do I have sitting around? How is my memory being used so far? So anytime you launch a Spark application, you can go to whatever host it is, 4040, and you get this UI. You can look at the storage page, and it will tell you, hey, you've got one RDD that's your data set. RDD stands for Resilient Distributed Data Set. Kind of just like your collection. Here's how, what a description of the data set, where it's stored, how much of it actually fit in memory, maybe it all didn't, how much room it takes up, where the data is living. Did it fit in memory, or does it fit on, or do we have to spill it to disk, et cetera, that kind of thing. So, if you're not sure, since you have to do this manually, you have to decide, this is a way for you to see, do I have, how much room am I using so far in the application? Okay, so this was the first pretty basic demo. Oh, I think I already made. Yeah, so I already kind of showed this, and we discussed this briefly. But one interesting thing is that Spark does it all lazily. So say I just did that filter command again. Nothing happened. Spark just tells me, okay, I understood you want that, and that's represented by another data set. But it hasn't done anything yet. You notice other times when it didn't work, a whole bunch of work happened. So Spark has an idea of there's two major types of operations. There's transformations, which take one RDD and convert it into another RDD. It's all it's a logical view of your data set. It's not really doing anything. But until you do an action, that's when Spark says, okay, you've queued up all these actions. How do I put these together? What's the right way to execute it? So after I do this, so let me take the output from that previous one and count it. Boom, then Spark goes and does some things and queues up tasks, sends them to the various nodes, and gives me the result. Same thing if I did the same thing again. Just again, nothing happened, right? And there it goes. Right?
About invalidating that cache, if I want to take it out.
Oh yeah, there's an unpersist method.
Okay.
Whoops. Sorry, let's see whether the UI actually updates. It does. Right. That's good. Thanks.
So what part of that data set is cached? Is this the one that's querying, or is it the entire set? You did count, so it pretty much took everything, or if you did a subset of it, then
So it's whatever you. So let me put it this way. So if let's start from that's a very good question. So lines was defined as basically the entire text file. Okay. So I'm explicitly defining this data set as the entire thing. There's no filtering. So I can cache this one. And that's going to be the whole thing. I can also make another one. Let's call it.
But at this point, it's not cached actually, right? But if
That's right. But yeah, it's a good question. I think my demo will answer. So maybe it won't. But let me try. So let me do this thing.
Yeah.
All the time. Filter down to just the info, right?
Yeah.
Okay, let's cache info only also. So okay, take a look at my UI. Nothing has been cached, right? Now if I do info only, that count. So if you recall, info only, it referenced lines which went to the data set.
Yeah.
But there were intermediate RDDs and they both got cached. And now you see both are in the UI, right? right? So Spark figures out, it doesn't do anything. Again, it builds up this lazy, transformation graph.
It's a pipeline that's built up,
Right.
and then it will
Right.
do the dependency and then.
Right. So you can cache whatever you want along the way. So if you want the whole data set cached, because it's going to be used some amount of time, but you also want some small data set because that's going to be referenced in a tight loop somewhere, you can also cache that. So one thing you may notice here is that, well, the first data set has a nice name. It told you what file. The second data set is called 8. It's not terribly useful for you, right? Well, that's because how does Spark know what you want to name it, right? Because you can do kind of arbitrary transformations, but I can do info lines that's a name. Now, the unfortunate thing is I needed to do that before I called cache. Before I actually evaluated it. So it's not going to update the UI now. But
Info only.
info.
Is there a tab complete and autocomplete
There-
with the shell?
There is. It's a little. It's slightly flaky. But it's the Scala shell also has tab complete and it kind of works. But as you nest things, and then the thing is that these other. So some of the stuff is Spark doing work in the background, like cleanup state, and that logging is just kind of interfering with the tab completion. So that's why this is kind of backfiring on me a little bit for the purposes of the demo. Anyway, and actually I don't even know why I bothered that because it's not actually going to update the UI because you want to. It's only before you actually have a stored in cache you need to set the name. But that way, that's actually a really important thing because otherwise, basically anytime you cache, you should do that because it's just too hard to figure out. Great question, actually. All right, so now the obligatory word count example because we can't have big data example without word count. So So let me just go from scratch here. So again, there's a little bit of Scala syntax here, which I'll explain. So the first thing I'm going to do is I'm going to make another RDD of words. So the first word happens to be the string 15 here. So there's all sorts of different operations you can do on these. Flat map, this comes from Scala. Scala uses flat map as an operation on collections. The idea is if you want, it's a one-to-many transformation. It's basically kind of like map and then flat, right? So I take one whole line of text, I convert it into an array of individual words, but now I want to flatten that, right? So it's still just back to a collection of individual words. So word count, all right? So what do I do here? So what I want to do is I want to, if you recall that map reduce graph, I want to create a key, right? I want to group all the words together and then just sum up how many of them occurred. So what I want to do is create first of all, a record for the word plus how many times it occurred. So far, all I know is that word occurred one time, right? I've only seen one record. But now I want to group those records together by key. So this is a reduce by key operation. And what it's going to give me is two sides. What's the count from one half of the data and what's the count from the other half of the data? Just kind of keep merging this together. So I've got A and a B. Okay. So again, a little bit of Scala syntax there. All I'm doing is I'm defining a function which takes two input arguments, A and B, adds them together. That's it. Right? Again, nothing's happened so far. But now I can tell, because this is a lazy transformation, I can tell Spark, okay, go. Collect is another one of these action operators, which makes things happen, which says, okay, after you run this, bring back all the data. Like, let me see the entire thing that you did. And so now I see, okay, Scala occurred 70 times, created occurred 11 times, et cetera, et cetera. All different words that occurred in my data set. And so, if I can just, okay. So I'm going to reuse this for a couple more interesting examples. Word count is almost too simple in Spark for it to be a worthwhile demo. So I'm going to do a couple more things. So I'm going to cache it and should know. Actually, I remember I put there we go. So, right, so what did I do? Let me go back to show you what I did. So I made word counts, again, just that RDD for each word, how many times it occurred. And then what I did is because word count is too simple, I wanted to see how many words occurred more than 100 times, right? Similar example that we've seen before. I didn't ask. Can everybody see this in the back? I realize all the action's happening on the bottom. Should I move it up? That'd be helpful. Yeah. All right. Let me just share my screen. I apologize for that. Better? Yeah? So similar thing, sorry, too much happening, but similar thing I was doing before. So word counts is now an RDD. Show you the type of it. So it's an RDD of a pair of things, a string and an int, right? For each word, how many times did it occur? And then I do a filter, a little bit of Scala magic. I wouldn't worry about that, but I'm taking a function which takes a word, how many times it occurred, saying if I only want those pairs where the count is greater than 100, how many words did that occur for? Did that happen for? It was 28. So now I might want to do, you might wonder, well, how many times did this occur for words that occurred 50 times? And how many for words that occurred more than 10 times? I don't know. You just do this over and over again. Like, I want a better way to do this. Why don't I just make a histogram? Let me find out how many words occurred one time, how many words occurred 2 times, et cetera, et cetera. So we can actually just do the exact same thing we did before. Again, we're going to, for each word and the number of times it occurred, we don't care about the words, that's irrelevant. We're going to say, okay, that count happened one time. Now count how many words occurred, with that particular time. Let me do the same thing again. And now we can do this all over again. Now I'm just going to look at it. This is, I wouldn't stress about this. I'm just going to use some Scala to print it out nicely. But I'm just going to grab the data for that histogram and then sort them and print them out. And then I can see that one word occurred 2,499 times, one word occurred 1,006 times, et cetera, et cetera. Right? Again, all pretty simple, pretty easy to do. And, you might not get the Scala syntax, but it still feels like something that's not too hard to do. And again, the same code would work here on my laptop, or if I'm growing a 100-node cluster. Or here we can look at what are the top words. Similar kind of thing. What I'm going to do is filter down to words which are over 100 times, collect them, sort them, and print them out. It's like empty strings, the most common. Just this is the name of the test suite I happened to be running when I created this log file. The log level, thread pool, stuff like that. So just again, it's a dumb logging file, but you can get the idea for what's going on. I think we've actually covered most of these examples, so I won't kind of belabor that. Any questions on that? That's I just want to give people a kind of a rough sense of what you can do with Spark. I know that gives you some sense of working with it and doing basics. I'm going to go into a little more detail now about what we did and how did that work. The questions are actually really good. Just in case my example backfired. Oh, this is one that I thought was interesting. So just, word count, like I said, it was almost too boring. It was this tiny amount of code. Actually, there's a little bit more in this example than we did because I'm also setting up the Spark context, which you have to do if it's not a Spark shell. I'm saving the data back out to HDFS just to make it a little more comparable to the MapReduce example. Oops. As you can see, there's just a lot more boilerplate here. For something so simple.
How is R integrated into this? Do they have a separate R?
So Spark R was very recently integrated into Spark. It had been developed, kind of independently for a while, but always in touch with the Spark program. But actually, I can't remember whether it was it in 1.3 or is it not until 1.4? It's just
That's the beginning of.
Right. So it wasn't in 1.3. Yeah. So actually, maybe I didn't mention this in Spark. Spark's already on release. Release 1.3 is already out. 1.4 is in probably within a month-ish. It's going to be releases in that.
Okay.
And Spark R will be there, but it's obviously it's brand new as part of Spark itself. It's been developed for some time. I don't know if that.
But it's the like that would, so you could use ours, all the library visualization, everything with data
Well,
into it.
Yes and no, right? So what can you do? You get an interface into Spark.
Okay.
You can interact with Spark from R, but and you can do, if you pull data out of Spark, then you can interact with R. This doesn't mean that every random package that you grab from R knows how to run on a cluster, because many of those algorithms are written to just sequentially scan data. So that's what I mean by yes and no. Like, yeah, there's integration, but R, when people talk about R, they really are talking about the ecosystem of all the packages. Right. Yeah.
Okay.
So yeah, I mentioned this, but just I want to really drill this point in. Just, how easy it was to develop that. Having that shell is a great tool, especially if you're kind of doing that first exploratory phase, kind of data sciencey type thing. And the other thing is that you don't need to worry about the details of the parallel distributed computing. The same code runs, even locally on one thread to maybe you just buy a really high horsepower machine. It's easy to get 32 cores, and then take the same code to a cluster of thousands of nodes. And it all works the same, except for some caveats, which I'm going to give you a little bit later when I get to them. So a little bit about how it works, some of the core concepts. So I mentioned RDDs. The idea is that you as the application developer, you only deal with it. It feels a lot like just a collection of records. But the way it works is that your data set is distributed parts, partitions. If you're familiar with Hadoop, it's a similar idea. And partitions live on different nodes out in your cluster. So one node will only have some portion of the data. And in fact, it may even have multiple partitions. This slide only shows one, but it could be that your RDD has a few partitions here, a few partitions there, and a few partitions everywhere. And each node only needs to worry about the data that's on that partition. If it's going to do a map, all it cares about is how do I take this subset of data and apply a map to this? How do I filter this data? That's all it cares about. And again, we talked about the fact that RDDs are logical. It's this lazy thing. They don't necessarily, they're not all out there.
So is that on disk? What were you showing on disk? Or
No, this is I'm fudging a little here. This is really kind of in between. A partition, so RDDs, they don't necessarily exist anywhere, right? They really are just a logical view. They might exist. So in the example that I had, if you remember, like my original data set was on disk, right? So maybe I have log files and a bunch of them, they exist in my cluster and you have different partitions existing on disk. But then I make another partition, which is another RDD, which is just to like map it. Let me parse something out of it or whatever, right? That RDD doesn't exist anywhere. But still, each node knows, in some sense of the word, that I own this partition of this RDD. I'm not going to create it, but I know that if somebody requests, the parsed version of the logs, I'm going to take the logs on disk and I'm going to parse it. Right? And I still, you need to tell me what to do after that, because that means nothing until you tell me, oh, and write it to disk, or and save it to memory, or and do a shuffle on it, or whatever. So it doesn't really exist in it. It's just sort of a concept that this node knows. This is how I would create, how I would
just build a pipeline of what to do.
Yeah,
to that,
yeah, right. I feel like I did not answer your question.
Well, so yeah, I don't quite follow. So is this like you're showing HDFS basically, just that you have the different blocks, or I guess I'm coming from that space, so I'm trying to now.
Maybe, so I tell you what, I have maybe, let me see if I answer it in a couple more slides, and then tell me again if I haven't got over this. It's definitely a really important concept about the fact that these are all anything. So, we talked about caching data in memory, that's really useful. Another important point here is that, remember MapReduce, which achieved fault tolerance via replication? Well, Spark takes a different tactic. I mean, you can use replication, actually, that is an option. But another idea is it just uses lineage, right? So if you remember, I had like my lines RDD and then just my info lines RDD. And let's suppose that one of the nodes went down, which had my info lines, my info only RDB. And so some of that data is just gone, right? It was supposed to be cached in memory, but now that node is unreachable. Well, what does it do? It says, okay, that's fine. Info came from the raw data, so I'll just go back to the raw data and recreate it. I don't need a replicate. I can just recreate the data from the source.
So it just goes out to one of the other, you're talking about on a cluster, so you go out to one of the other nodes and just rebuild the data.
That's right, yeah, exactly. Okay, so I hope this slide will help answer your question. May not. So we've talked about this idea of building this transformation, this graph of all these operations. And this is hopefully meant to a diagram of how this works. So here's I didn't show an example this complicated, but you could have some data set where you start with, or some pipeline where you start with, one data set to do a map transformation, then you group it together in some way, then you have some totally independent data source which you need to do a map and a filter on, and then you join these two together, and finally you take the results. Right? Each of these operations is a transformation, so Spark's going to do absolutely nothing until you get to that final take. Take is the action where the developer is saying, okay, actually I need you to deliver the results back to me. But as you do this map and this filter, Spark's just going to say, okay, I've made this logical RDB, but I haven't done anything yet. Right? Same with the operations on the top. So along the way, some node here, right? It knows, okay, I'm responsible for this little portion. Right? When you say, okay, take this data set and map it there, this partition, each one of these little factors, so this is one RDB, and each of these is one partition in there. Some node knows it's responsible for that partition, but it still doesn't do anything. Right? And in fact, what it's going to do, this one, let's say it's read from disk. It's going to read this from disk, it's going to do the map, and it's immediately going to apply the filter. So it never sort of creates this thing, if that makes sense. It's really just this logical concept. If I helped or not?
I'm still not quite there, but so is the RDB just really a definition of what the operation is?
That's exactly. That is exactly
where the data came
right.
from that this node is going to
handle. A definition of what operation it is, where the data came from, and also sometimes how the data is distributed across the cluster as well. Which you, the user, don't necessarily need to worry about, but that's an important part of its internal system. It knows, okay, the data is partitioned this way, and here's how an input partition goes to an output partition. Right? Even though a partition doesn't necessarily exist anywhere. Right? There's only certain things that exist. But yeah, that's exactly right.
And don't act on it until.
Sorry?
And don't act on it until
Exactly. Yeah.
Like call by need.
Yeah.
Rather than value or reference.
Definitely a fair question. I think this is tough coming from me. I went through this too. Yeah.
More of like a Stalia question, but I do Haskell, right?
Okay.
So they have like a notion of a monad.
Yeah,
Is that kind of what's going on?
Scala does. Spark kind of does.
With all the lazy evals.
Yeah, but it's not. It's not. I mean, I guess that there's similarities, but it's not. Yeah. I don't know how much to say. It doesn't there are parts. It's definitely made to mimic the Scala standard library in the way it chooses map and filter and flat map and so on. But it also doesn't quite do everything that the Scala standard library does, and all of the support it has for doesn't necessarily. I don't know. I'm giving you a very hand-wavy answer, I guess, but you guys just need to see. Okay. All right. So we're on to a little bit more advanced stuff. Definitely, yeah. Your questions are great. Feel free to keep interrupting. Good stuff. I'm happy that I made it this far. So again, there's this huge API, right? So Hadoop gives you map and reduce, right? But Spark gives you all these different operations. You can map and filter, and you can group, and you can reduce, and you can union, and join, and so on. I guess actually, we map reduce, you can join too. But, so you do have a lot more things. Now the thing is, it's sometimes a bit overwhelming, but I think to know your way around this is just a couple of key concepts to keep in mind, which I'm going to try to go through, rather than sort of learning each one by one, because it's important to understand what's going on, not necessarily just is this important, but how does this fit into sort of doing something efficiently in a distributed manner? And in particular, what I mean by that is when I was talking about, you write something, you test it out in your local machine, it works, so therefore it's going to work on a cluster. Well, it might, or you might have designed something in a way that it's really just not a well-designed distributed algorithm, and that's why you need to know something more. So for people who have a background with you, this is just kind of like a list of keywords. I'm not going to go into these in detail. But if you are familiar with this stuff from working with MapReduce, it's kind of the same problems. If you want to minimize data volume, you're going to use a format like Avro or Parquet or something. You're going to use good serialization because Java serialization is really bloated. Yeah, some of these other things. If you have seen them before, you know what I'm talking about. If not, you can look them up. But this one's interesting, I think. So when I was talking about test it out on your local machine but maybe it'll work in a big cluster. So I actually kind of cheated an example that I did. So I said, oh, my log parsing, that will just work if I actually didn't do this example. This was one of the examples I did. But imagine that I did an example where I did a reduce by key by the log level, right? So I wanted to count how many records had info, how many records were error, how many records were worn. So that would kind of work if I did it at big scale. The problem is that there were only 3 groups. So when I do my reduce by key, all that data is only going to go, if I start with 100 terabytes of logs, well sure, that first phase will be fine, but eventually I will only be sending that data to 3 nodes because there's only 3 keys. There's only info, worn, and error in that example file that I had.
Better, like, let's say if your data set is long enough, you can be grouping by like the date, not necessarily the time. But
There's all sorts of techniques. And I think it's probably more advanced than we chat about it a bit more. But I'd say it's sort of like the same lessons from MapReduce. And I'm gonna talk a little bit more about something else to give you as well here. So another really important point is that part of this lazy evaluation means that Spark can be really smart about how it does these things. So if you wrote your code this way in Hadoop, sometimes it's convenient for you to think about a map and a filter as separate because it gives you abstraction, right? You're software engineers, you want somebody to work on a map component, somebody to work on a filter component, you can test them independently, whatever, right? It's easier to reason about. But you wouldn't do that in Hadoop because you'd have to do 2 different phases. But Spark gives you the flexibility to write them independently and just join them together. And it's smart. It says, this intermediate stage, it kind of doesn't even exist. There's no serialization. There's no I/O to disk, even to memory. It's totally pipelined. So one record goes through the map, immediately gets filtered, and does that. It's not like it buffers a whole bunch of records together after mapping, then it does the filtering. It just, it pipelines all that work. But where things get expensive is shuffles, right? So anytime you're doing something like a group by key or a reduce by key or a join, this is when all the nodes have to talk to each other. Same story as Hadoop. Nothing's really changed there. Of course, Spark has claims to be more efficient and everything. It's definitely something that's worked on, but it's still the bottleneck, right? That you should be very clear about that. This step, any of these steps that all the nodes are talking to each other, it's really expensive. You've got to serialize the data. You've got to write it to disk. You've got to transfer it over the network and then deserialize it again. And often, all that also means there's like all sorts of buffers behind the scenes, and there's contention for memory. So that's really where you want to try to minimize the amount of work you do. So I want to show you. Let me go back to one example. I know I'm nearly out of time, but I think this will be one good last example. So I'm gonna. I'd say just don't worry about what I've done so far is I just kind of parse those log lines. The code there is just like regular expressions and some Scala pattern matching. It's not really important. All that, just to give you an example of what I have now is an RDB of just parsed this kind of container class. So log line has the time separated out, the thread name separated out, what the log level is, so I can do. So I just have, this is the only important point. I've just separated out what the log level is. So let's say now I wanted to count how many happened with each different log level. So I can do kind of what you would expect. I take the level, I give it a count of 1, I do my same old reduce by key example, and then I collect them. So there were 4 error records, 497 info records, and 11 warning records. But I could do this another way. Another thing that I could do is I could use a group by key. I could say, instead of just doing those sums together, why don't you take all these level records, put them together. So stick all the info records together, stick all the error records together, stick all the count records together, and then just, look at how many records you have, and that's this, counts.sum, and you collect on that. It's still going to give me the same answer, but there is a, let me show you. Jump rate. Actually, another thing this UI gives you is a detailed view for tasks of kind of what went on when you did that computation. So you can see for each stage how many tasks you completed, how long they took, and importantly, the most interesting thing is how much data was read by showing how long each task took. So you can compare different versions to see. And so when I did a reduce by key, it was basically you're doing this style operation, right? Where each node needs to talk to all the other nodes. With a reduce by key, before you transfer the data, each node is going to combine all those counts. It's going to say, I have, instead of transmitting all the info records and all the error records and all the warn records, it's going to first sum them all together and say, I've got 3 error records, 50 info records, 2 warn records. I transmit a much smaller amount of information, which means that you just have a lower overhead there. And go back. So here's the kind of key takeaway. When I did this with a reduce by key, the shuffling was only 3 kilobytes. When I did it with group by key, it was 142 kilobytes. This might have been actually a slightly different data set, but the point is the same. It just has a higher overhead. And this is really one of the most expensive things, so this is something you really want to keep.
There are other profiling tools available?
This is what there is now. So the thing is, there's a lot of work being done to kind of give you better stuff. So this same information is available in a few different ways. So you can also create a Spark, what's called a Spark listener. So when you can say, just ask something, like every time a stage completes, just give me some information about it, and I can do whatever it wants. And so I have used this in the past running pipelines, is to do this and have it just kind of say every time, like, there's more data being shuffled than I thought, or tasks computed at very different times, right? Some finished fast and some took way, way longer. Those are just kind of red flags. So something that you just kind of like alert me, like, hey, you should go look at step 17. It doesn't look right. And sometimes you'd be like, that's kind of I know, I'm stuck with that. And sometimes I'm like, oh, that was a surprise. I did not expect that. There's other stuff being developed. I don't know if there's anything that's super great right now. I think I'm nearly out of time, so I'm gonna skip what I have left. There's nothing really too exciting here. Let me just leave you with a couple of pointers for some resources, and then we can do any more questions. So first of all, Spark is super active. It's like a ton of contributors, a ton of people involved in the project. The community is really, really helpful, so you can go to that URL and just join the mailing lists. We get lots of information there. There's a Spark user meetup in Chicago. I'm actually going to be speaking at the next one coincidentally, which is next Wednesday. I'm going to talk about more advanced stuff. This was meant to be a very much an introduction, of course, but kind of more of like what worked and what didn't as I was building big pipelines. And I don't know how much I'm probably going to take, but a little more in depth. That I just found out the meetup is full, but I would suggest getting on the wait list. People don't show up. Normally, Demoppler runs it like a day before. He'll tell people, hey, if you're not coming, make room. Demoppler also wrote he kind of put together a self-paced Spark workshop. You can just check out this project on GitHub and work your way through it, and that's good. There's some other good. I think this is a pretty good presentation about how to write Spark jobs. It says some of the same stuff I did, but it's good to get a different take on the same stuff, I think. And also Sandy from Cloudera has this great series. He's done a lot of work helping people kind of get their jobs to scale and how to tune your jobs. And I'll read there a few more next questions. Yeah.
How hard is it to install from the Tarball if you already have a Hadoop cluster going? Like your database level?
I mean, it's pretty easy. Well, I don't know. Maybe yours is more than
So you're saying if you already have a Hadoop cluster that is running, how easy to install?
Yeah.
It's a great question. So usually if you install, let's say, Cloudera distribution Hadoop, it actually comes part of it. You don't actually have to do any extra installation. But let's say you are just using vanilla Hadoop and then you want to run Spark from scratch, then it should be still straightforward. It just needs to be able to find the Hadoop configuration files, so you can talk to HDFS and stuff.
It's mostly just pushing a few files out to every node in the cluster.
Yeah, and then you have different configurations. Yeah.
Well, it's a little bit more than Hyperpig. Because Hyperpig don't have to go out to every node. Okay.
Yeah, that's right. It does need it.
All right.
But if you want to play around and download, it's actually free. And you can download this and write on even 10, 50 nodes of clusters for free.
Yeah, well, it's right on Hadoop, or it's right on Apache, right?
Yeah.
Right.
Yeah, and I should also add that another platform for it too. It's easy to sign up, but that's a way to get started. And I mean, that's the other great thing about the community. There's like some subset of things which I know about. Like if you that's what I wouldn't know anything about it. I don't use it, but other people do. So we'll find someone to answer your questions. All right, great. Thanks, everyone.